Alright, so this presentation is going to be a review of some energy and power basics. So we'll go over the difference between energy and power, first and second law of thermodynamics, different types of energy use in a building, potential and kinetic energy, and different energy units. This is a review from all of Energy 101, so you should know all of this already. So this I'll go through it rather quickly. So let's start with energy and power. So energy is defined as the ability to do work. And this, from a physics perspective, work is just the application of force across a distance. It's basically the moving of energy from one place to another. Okay, so work is required to move energy around. The most important thing to think, practically speaking, is that energy sort of makes things happen. It causes everything around us to happen. So anything that human senses can sense requires energy. Light requires energy, sound waves require energy, motion requires energy, heat requires energy, okay? And energy is in everything around us all the time. So anything that's made of matter, which again is everything that humans can sense, it all has energy. So if you look around you, whatever is in the room around you right now, so you can see behind me, I have a ceiling fan up there, that's made of matter, so those molecules atoms are being held together by chemical bonds. That's chemical energy. The atoms in there have nuclei, that has nuclear energy. It has temperature, so it's radiating energy. So everything around you all the time has energy and is using energy. So power, on the other hand, is the rate at which energy is converted or provided. Conventionally, we think about providing, but really it's how the rate at which energy is converted. Okay, so we convert energy from one form to another, and that the rate at which that happens is power, right? So again, this is a review. Everything around us uses power, so you can think of the power of a battery, like how much electrical energy chemical converts to electrical. The sun converts nuclear energy to radiant energy. The human body has a certain power rating. That's the Delaware Tech Stanton campus, so they use a certain amount of power. The Earth uses power. So all of these, you can look at the energy and power. Okay, so power is the rate at which energy is being converted, and you can take just about anything, and it's going to be converting some form of energy. If nothing else, it's radiating thermal energy in all directions, which is using power. Okay, so some basics about the laws of thermodynamics. The first law of thermodynamics, first of all, the thermodynamics is the study of the effects of work, heat, and energy on a system. That's a little bit fancy. Really, just think about thermodynamics as the study of how energy moves in and around systems. So as energy auditors, even though we don't normally think of it, we actually are dealing in thermodynamics all the time. We're looking at how heat energy is used to heat a building, how we're moving heat energy from a building. We're looking at how much electricity lights are using. All of that involves thermodynamics because it's the study of how energy is moving around systems. So the first law of thermodynamics, and you should know this by now, and you want to jot this down, the first law is that energy can't be created or destroyed, right? It only changes form. So energy never goes anywhere. It's the energy that is in the universe now has always been there since the universe began. It just may have been in a different form. Okay? So when we say we use energy, like a light, a light uses energy or a light bulb uses energy, really what you're saying is that light bulb is converting energy from one form to another. And then after it's converted, it's another form, and it never disappears. So most of it ends up as heat. Some of it ends up as light. Maybe there's some vibrational energy that's converted into whatever. But the key is that because of the first law of thermodynamics, all of the electricity used in light doesn't disappear. It just is converted to another form, and then it stays forever. So it never disappears. We've done this before, or we've looked at this before. But let's think about the second law of thermodynamics. The second law of thermodynamics refers to entropy. And practically speaking, what the second law dictates is that when you convert energy from one form to another, it becomes less useful. Okay, so the entropy increases. Entropy is a measure of the sort of chaos of the system. So you think you convert, like in the light bulb, electricity is converted to light and heat. Once that light and heat escapes, like, it's really hard to recapture because it has high entropy. Okay, so it's not terribly useful. I mean, heat energy, it warms. You can use it, but like you can't. It's hard to recapture that thermal energy. Whereas electrical energy, you can store it, you can take it from place to place, and very little of its loss. It's a lower entropy energy source. So anytime you convert from one to another, it converts to sort of a lower form, if you will, or less useful energy. That's your second law. That also is why heat travels from areas of high temperature to low temperature, which is something that we'll talk about in more detail later. This is really a review, so I'm going to go over this really quickly. You have your two major types of energy. You have your potential and kinetic. So potential is really stored energy, right? Kinetic is energy of motion. The main types of potential energy, you have nuclear, chemical, mechanical, gravitational. So nuclear is the energy held inside it that holds the nucleus of atoms together. So everything around you has nuclear energy. Most of it we can't use, but it does have nuclear potential energy. Chemical energy are the energy in the chemical bonds that hold molecules together. So H2O, right? So water, a water molecule. There's, you have your two hydrogen and one oxygen. Well, there's chemical bonds that hold those together. If you break them, excuse me, you release that energy. And we actually talk about that when we look at latent heat transfer. But you could, anything like, another really important form of that is fossil fuels, right? So coal, oil, natural gas. The energy you extract from that when you burn it is actually the chemical energy that's inside of the molecules of that. And when you burn wood in a fire, that's releasing that chemical energy. That's holding the carbon, mostly carbon, atoms together. So mechanical potential, you can think of as like a wound up spring, or if you stretch a rubber band and you hold it out there, that has mechanical potential. If you let it go, it'll can be converted to kinetic. Gravitational is just if anything above the ground has gravitational energy. If you hold anything, right? So like my little pen here, this has gravitational potential energy. If you can see my screen, when I drop it, that potential energy is converted to kinetic energy when it falls to the ground. So kinetic energy is energy of motion. We have electrical, which is the moving of electrons. Electromagnetic and thermal, I'll come back to those. Then we have motion energy, which is just physical motion, right? So like if I would throw this pen, or that spinning fan blades behind me, that's mechanical kinetic, or motion kinetic. And then sonic are the sound waves that are, sound waves are a form of energy. I want to quickly go over, let me see if I can get this to work. Electromagnetic versus thermal. Let's see if I can. Okay, so thermal energy. So let me try to do this with my finger. Shoot. Thermal energy. Okay. Everything above absolute zero has thermal energy. Thermal energy is just the vibrating of the molecules in a substance. So look around you. Everything around you right now, because it has temperature above absolute zero, the molecules, if you could shrink yourself down to molecular level, you would see that the molecules are actually vibrating. You just can't perceive them, the naked eye, you can't perceive them. Yet everything has vibrating molecules. The wall behind me, the shelf behind me, the glasses on my face, this pen, the computer in front of you, whatever. All of it, the molecules are actually vibrating at a molecular level. That vibration is thermal energy. Okay, so that vibration is thermal energy. So it's just and so if I take like a, let's say this was a cold, you can see my screen, a cold water bottle, and you take your warm hand and you put it against the cold water bottle, okay? What happens is your hand, because it's warmer, is vibrating more. It has more thermal kinetic energy, okay? And when you put it against the water bottle, the water bottle has less thermal energy on average. Okay, so the molecules are not vibrating as much as your hand. And so when you put your hand on there, the cold sensation that you feel is actually the thermal energy from your hand being physically transferred to the water bottle. And that's going to happen, whichever substance is warmer is going to transfer some of that thermal energy to the other substance. Okay? So thermal, again, is the vibrating molecules. Electromagnetic or radiant, which is also known as radiant energy. Okay? So radiant energy, let me tell you, radiant. Sorry, I'm using my finger here. So radiant energy is the same as electromagnetic. So radiant energy, everything that has any temperature at all radiates energy in all directions, and that travels in these weird transverse waves. So it's kind of like one wave. I can't really draw it, but if you can imagine waves at 90 degrees kind of traveling like that, emanating out from all objects, right? So if you have a doesn't matter, anything, right, like a little 10, that's actually radiating energy in all directions. Everything around you is radiating energy all the time. Okay, so that's radiant electromagnetic. Want to be really clear about that, because a lot of people think radiant energy, they conflate that with thermal, because they think thermal is heat and it's radiating heat. That's not the case. Radiant energy travels outward in waves, whereas thermal energy is the vibration of the molecules in the substance itself. Okay? So that's really, really important. So sunlight, for example, that comes through the window, that's all radiant energy, because it's waves just traveling in through space, and then it makes it through the Earth's atmosphere and to you. Okay? So that's radiant versus thermal. Okay, now some of the more common energy units that we will encounter in this class are your BTU, your kilowatt hours, 100 cubic feet of natural gas, gallon of fuel oil, and gallon of propane. So BTU is our basic unit of energy in the U.S. And is defined, and you should write this down as, it's defined as the amount of energy required to heat up 1 pound of water at 1 degree Fahrenheit. For our purposes, it doesn't matter if the water is, let's say you have 1 pound of water, that's 100 degrees. If you add 1 BTU to it, it's going to be 101 degrees. In order to drop it to 99 degrees, you need to subtract 1 BTU. Okay, so 1 BTU per pound. If you have 5 pounds of water, actually let's say you have 1 gallon of water, which is about 8 pounds. So you have 8 pounds of water at, I don't know, 50 degrees. If you want to increase that by 1 degree, okay, you have 8 pounds. To go 1 degree requires 8 BTUs, okay, and so on. So it's a 1-to-1. If you want to think about like sort of how to wrap your mind around it, it's about, if you take a wooden match, you let it burn all the way down, that's about 1 BTU worth of heat. You definitely need to know that an MMBTU is the abbreviation for 1 million BTUs. Okay, so MMBTU is something you see in the energy field all the time, and that's 1 million BTUs. A kilowatt hour is our electrical energy unit, 3,412 BTUs. We have CCFs, which is natural gas. That's 100 cubic feet of natural gas. That's what the CCF stands for, 100 cubic feet. Gallon of fuel oil, and propane. Now each of these have different BTU conversions. These are not universal. Okay, so it depends on how pure the natural gas is, how pure the fuel oil is. So fuel oil is heating oil, by the way. It's also the same as diesel gasoline, and propane. So these can vary a little bit in their BTU content, whereas a kilowatt hour is exactly 3,412. Okay. So those are our basic energy units we'll encounter. Power units, there's less. We have the watt is the big one that we're going to use, and BTU per hour is another one. We won't really encounter horsepower, but it's worth knowing. So watt is it's a joule per second, or you can think of it as a watt hour per hour. or 1 kilowatt hour, or well, it's 1 kilowatt hour is 1,000 watt hours per hour, right? So the way you'll usually use watts is you'll take the wattage of an appliance, you multiply it times time, and that gives you your energy use, right? So 100 watt appliance for 1 hour is 100 watt hours. A BTU per hour, so we'll use this a lot for furnaces, but they also use this for air conditioners and heat pumps. So a BTU per hour, which is confusingly usually just abbreviated as BTU, so like a 50,000 BTU air conditioner means it's 50,000 BTU per hour air conditioner, which means you can remove about 50,000 BTUs every hour with that air conditioner. It depends on how cold or warm it is outside, but that's what that means. A 100,000 BTU furnace is a furnace that can burn through 100,000 BTUs of fuel in an hour. Not release, because it's less than 100% efficient, but that's its input. Okay. An abbreviation that you should know is MBH, which is used a lot in the energy industry. That means 1,000 BTUs per hour. Okay, so if you have a 100,000 BTU per hour furnace, that means it can burn through 100,000 BTUs every hour, and that's 100 MBH furnace. And again, you are going to get less heat out than that because of the second law of thermodynamics. It's got to be less than 100% efficient. Horsepower, on the other hand, is something we won't really use that much, but it's equal to 746 watts. This is an electrical power rating. At least that's how we use it. You could, as you know, I'm sure you know, car engines are rated in horsepower, so that's different, but it's still equivalent to 746 watts. So it's important to know, and I'm sure you know, that you can convert any energy unit into any other energy unit as long as you have this conversion factor. And you can convert a power unit into another power unit as long as you have a conversion factor, which we'll do much less of. But certainly you should know, it should be second nature to you at this point, converting one energy unit into another unit. Okay, so that's your introduction, your reintroduction, I guess, to energy and power. So we went over the difference between energy and power, the first and second law of thermodynamics, the basic types of energy the building uses. We went over potential and kinetic energy and examples of each, and then also went over the basic energy and power units.